Hey everybody, this is Larry. This is me going with Q4 of the weekly contest for 25. Maximize sum of rates after edge removals. Hit the like button and the subscribe button, join me on Discord. Let me know what you think about this one. So this one, I did it with memorization, but you can think about it also with dynamic programming. Or maybe just kind of almost like a topological sort, honestly. If you do it correctly, I think you don't need memorization. You could do it with as a topological sort, and as a result, this is going to be pretty performant. Yeah. Anyway, the key idea here is that if you look at each tree, there are really only two states. I'm thinking about drawing it, but I don't even think it's that necessary, right? Each node, keeping in mind that you don't need to try every node as the root. I think that's key number one, is that this tree, you only have to solve it for one node, and that will be good enough, right? That's key one, which, I don't know, maybe it's obvious, but sometimes I feel like for me, myself, I second guess needing it and checking for all of it. But I don't think that is necessary for this particular problem. And the reason why this isn't necessary is because the invariants don't change, right? You're solving the same problem with the same root, right? The same edges should be removed. Okay. Yeah, and then after that, then now you n is pretty big, right? N is 10 to the 5th, so you know that you want to do something like linear-ish, n log n-ish, right? Like something faster than n squared in any case. And yeah, but for this one, I think the key thing is realizing that you could solve for each subtree, right? If you solve for each subtree, you can kind of, because every impact is localized. And what I mean by that is that if you look at this node, right, this tree, what node 2 does not matter to node 0, right? The only thing that matters is whether node 0, if we're going down, we move to the node connecting to 2. It doesn't matter which it doesn't matter what 2 did or does not. There's no global things to localize, optimized, you know. It's just whether for 0, whether I should, I have too many edges, I have to remove some. That is basically it. So the tricky thing about this one is, of course, you have to consider the parent. What if I have to, like, return whether how do we consider the parent? Well, the thing is that in this particular problem, there are only two cases. Is whether, and the parent can decide which one is better, which is that in a brute force kind of way, whether you remove the parent edge. That is basically the idea, right? Yeah. So basically, for each node, we decide whether we remove the edge to the next node, and then for each node, we also know whether we have to consider the parent or not. And we don't decide based on that. We just do it both ways because there are only two decisions, right? Whether we have a parent and we don't. If we have a parent, we do some math. If we don't have a parent, we do another math. And that's really the idea for this one. And then you kind of return it up. And then the key idea, the second key idea after that is that the parent, because everything is localized, I don't have to care about how my child reacts. I don't have to care about how my parents react because I'm just going to give them everything I know, which is whether you care about me or not, and remove that edge. Wow, that got really personal. But yeah, so everything is localized in that way, and that allows you to be greedy. And what that means is that here, we know the impact of removing every edge. Let's say, this is not a good example for it, but let's say, okay, maybe I will draw something out. Hang on really quick. I have to put it on the screen because that would be helpful. Yeah, so you have nodes, right? And it's not a binary node. But for example, let's say k is equal to 2. That means that for this node, well, what happens? That means that we have 4 children and we can only keep 2, right? And in a greedy kind of way, so we return, okay. So for this node, you can say if you keep, I'm going to put in a tuple of, to make it short, we're going to make a tuple of to keep to drop, right? And that's the cost of keeping and cost of dropping. So it's going to say, okay, well, I'm going to return some k sub I, j sub I, right? Or d sub I to the parent. And then now here we know that, well, because k is equal to 2, but we have 4 edges, right, going down, we can only, we have to remove 2, right? Have to remove 4 minus k, which is 2 nodes, right? And the way that we keep it is we just do the math, right? We go, okay, well, if it's, and you could do this with sorting, right? Or maybe I guess with a k sort or k heap, maybe that's a little bit better, but it's fine. I don't think you have to optimize that much. But yeah, because basically here, this is the cost to keep, this is the cost to drop, and so then now we would sort by the cost of keeping, or depending on how you want to do it, but you want to minimize cost of keeping minus the cost of dropping. This is not a j. Why did I write it down? It's just poor I. So we could sort by this, because then now this function is the cost of dropping, right? And because we have to drop 2, we want to minimize the cost of dropping, so we want to minimize this thing, right? And that's really the idea, to figure out, okay, well, so we keep we drop the 2 that are the cheapest to drop, and then the rest we keep, or we could drop more if we want. If it's cheaper to drop them, then we will drop them. So that's really the idea behind this problem, and then we'll explain it in code. And really in code, it is kind of how I talk about it, because that's how I thought about it. Yeah. So first, yeah. So here we have a goal function, and actually, yeah, I also wrote notes to remind myself, because it's very easy to remember. But node is the current node, parent is the parent node, previous is whether the parent match edge is removed. If not, we have to consider an additional edge to remove, maybe, right? And this goal function is a terrible name. Given these constraints, it returns the cost, the min cost of this node keeping to the constraints of less than equal to k, with the parent's connection at previous, right? So that's really the idea for this one. And here we just get the deltas. We'll go over this part in a second, but assume that we will get the calculations for each children node. And the reason why I did it this way so that I can cache it, but it's not really I don't think it's a big deal, but because this is cached anyway. So at most you do twice the work, but I don't want to do twice the work because Leetcode is slow. So I just cache this as well. But yeah, so the degree is equal to the number of children, right? If we count the parent, then we have one more degree. If we don't count the parent, then we don't have a, so yeah. And delta is equal to degrees minus k. So delta is the number of things we have to remove, right? And then we just kind of do a I don't know why I name it A, because I used to use R for results, but then I already used it here. That's why. But yeah, basically now we have to remove delta items. So let's go through all the children and sum up the cost, right? So in this case, A is just a sum, right? So the first delta items, we always have to take the keep. This might not look like anything, and you're right. The reason is because we'll go over the other part soon and we'll come back. But yeah, but basically this is the cost of keeping. Oh, sorry, this is the cost of removal. We have to remove this. It's cheaper for us if we remove this on a global level because of the delta. So we will have to remove this for a better sum. Here, you can actually represent in these ways. So here, the rest we can keep or not keep depending on what is cheaper. Yeah, and the reason is because it may propagate in the future, in theory, right? Because if you remove something, then maybe now the children can have an additional thing to keep, which may be cheaper. And then that leads on a cascading kind of thing. But so that's why we want to take the min of these. We want to keep or not keep depending on what is cheaper for the rest. Because we don't have to keep everything. We just take what is cheaper. And yeah, and then we sum that up. And again, we'll go over that in a sec. And then we just return the cost. And this basically returns the cost of this node, the minimum cost. And for this one, I know that you're supposed to maximize the score. I minimize the removal of the edges. So it's about the same thing. You probably can rewrite this in a cleaner way, but that's why I have a total minus R, because R is the minimum cost that we're removing. So total is going to be the sum of all the edges, which we have here, and then we removed some stuff. Oh yeah, I also set up the adjacency list. Okay. And then get deltas is the thing that we talked about. Again, I added comments because I end up wait. Okay, yeah, I was just making sure that I remove my drawing because I feel like I sometimes remove it. But yeah, I took 35 minutes, so I just have time to add in comments because you could watch the live portion of it. I was very frustrated with myself because I keep on kind of running into small, silly things. But yeah. But yeah, and then here, delta is removed. I did it with, okay, so this is the cost. So this is for each children, whereas now you go to parent, the cost of removing minus the cost of keeping, right? Because we're forced to remove, so we want to choose the people in which it gives us the benefit of the greatest removal. So here we have 3 items. We have delta, which is the cost that allows us to sort. The cost of removing, which is, well, now we don't have to consider the parent, so that's the recursion that goes back to this function, right? This is the current node. This is now the node is going to be the parent node. This is the children node, and then yeah, we're removing it. So that means that this is previous is going to be true, and then we add the cost of actually removing it, which is just W, which is what we get as input. And else, this is the cost of keeping, which is that we don't get we have a force flag here, and yeah, just setting up the constraints, and then we sort. And that's pretty much it. In the front are the mins to remove because it gives us the biggest benefit, right? Because it's removing minus keeping, and it is what we have here. So yeah, and that's pretty much it. Yeah, so there is this sorting thing. And in the worst case, you're gonna have a tree or a star graph, and therefore you sort n log n, or you sort n items, which makes it n log n. So this is gonna be a reverse n log n. Right, this entire algorithm, and because this is just linear-ish, right, assuming that the get deltas is fast enough. But you can split that up, but in the worst case, it's still going to be sorting most. It's going to be n log n. So yeah, that's all I have for this one. I'll go over it one more time. This is the code to set up adjacency list, setting up total, right? And then, yeah, and then we have the recursion, which looks over the node, the parent, and the previous. So we set this all up, right? Remember that we have to force to give the first delta items. Here we could keep or not keep, it doesn't really matter. So yeah. And then we also get the deltas, which allow us to do, so this function calls this function, and this function calls this function to get the deltas. The reason is just for caching reasons. And yeah, and we already talked about this, so that's pretty much it. And yeah, that's all I have for this one. Let me know what you think. Thanks for watching. And yeah, you could watch me bang my head on this problem. Because the thing is that for this one, I had the general idea pretty quickly, maybe like 3-4 minutes in, and it took me like half an hour to implement correctly, which is a mess. So I don't know. It is what it is, but you can watch it and see if you can learn something from it. I don't know. Learn that I'm an idiot maybe, but you could watch that next. Oh, YOLO. Super not confident nowadays. Okay. Just no confidence these days. Okay. Did they fix it? Did anyone get, oh, people already got 2 Qs. I got 3 Qs, but I have long answers, so that's not great. Alright, whatever, let's focus. 7 people got it already. Maybe I could be the, well, it's hard to be the 8th, but I'll be the next one. Alright. Alright. Undirected tree, there are edges, okay. We'll zoom in. Each node has an edge with at most k other nodes where k is given. Okay. The sum of the weights of the remaining edges is maximized. What does this mean? So 2 means that each node, so the degree is at most 2 of every node is what it's saying, right? It is a tree. To the 5th, okay. So the number of edges, okay. What would we look like? I don't know how to do it yet, just in case you're wondering. People knew how to do it very quickly, including ChatGPT probably. K is big, N is big, so you want linear time or N log N. Okay, recursion. What would recursion look like? And the star graph thing is kind of weird, so we have to make sure that, I think the naive DP makes sense, but the star graph is going to be wrong for it. Is it? Oh yeah, no, the star graph is fine. Well, how do you even do it? DP. Sorting DP, greedy. We know what we have to keep. So then we get the delta of keeping and not keeping this edge for each node, right? Because each node you have to care about it, I think. Something like that maybe. I don't know. Is it true? I don't know. So with the current node and where the previous or not. So then now, and parent just because. We're only going to do it top down once, I think. Hopefully that's good enough. Yeah. So basically the delta, right? So you have two choices. You have take this node, oops, or not take this node. So if you remove this node, you don't get the rate. We can minimize it, doesn't matter. So okay, fine. So you remove So you remove it, then you add W, otherwise you don't. So then it is going to be I don't know that this works. Can you do it this way? Can you do this in a greedy way? I don't know. I see. Maybe. I don't know, to be honest. Okay, then. Yeah, this is maybe I should call keep. Okay. I'm doing something that I think there's an optimization, but I don't want to do it optimized yet. It's at most 2 times too slow. We'll see. I don't know if you even know if this is right. Okay, maybe I could do it this way. Where's my mouse wonky? That's not the tricky part, right? Okay, I messed up. I mean, this is fine, but this is not enough. What I want is actually yeah, I'm copying pasting, but not actually. Okay. So smallest is at the end. It's removing mine. I hope we keep the beginning. I think that's maybe the idea, but maybe I'm wrong. If previous is removed, then this node is going to be equal to this, right? And then if just get delta. I took it out and then I forgot what we say it was. Damn it. I'm just being silly. Go reparent true is removing, so then you add the cost of removing, and we're trying to minimize the cost, I guess, minus keeping. Okay. So we want to remove, so we always going to be sort, okay. Okay. So then degrees minus k is the numbers that we have to remove. So yeah, and then if not previous, then we have to count the parent. So we add 1 just for keeping it. And then delta is going to be if delta is greater than 0, then we want to take the sum of is 0. Yeah, I think that's right. Okay. Oh, I already wrote that, right? Oh no, did I delete it? Why would I delete it? Oh no, I didn't. That was for a different problem. Yeah. I don't think this is right. I think we have to do some maps, but I just want to see if it works. Okay. Do I have no base case? Why would this be infinite? Renode. Oh, if v is not equal to parent, very obvious thing. -4 and 5, that's probably not right, but that is on the sum, right? So, okay. $20.75, nope. Is it minus? This is just wrong. Okay. Okay, this is so then we want to remove the min, so that's going to be the min. Right? I think this is more right, but I'm off by 1 maybe. Or off by something, off by a lot. Alright, time to stop guessing. The code feels right, so then what is the reason here, right? Yeah. Oh, I named 2 things the same because I am a silly boy. K is equal to 2, right? So if it's true, 0, okay, what? Node 1 is going to be 0 no matter what, that's fine. Okay, what is the sum? We have 6, 12, 24, right? So we, is that 18, 20, 24, yeah. Why don't we move to 2? Right? Okay. I feel like we're close, so hopefully we'll get to it. A lot of people is getting it. I mean, I feel like I'm close, but these days, clearly not. Alright, so 0, we move to the 2. 2 we remove, it's going to be 0. If we don't remove, it's 6. So if we don't remove this, we have to remove the 6, which makes sense. So then 2 is going to be 0. That makes sense. This makes sense. So why would you not go that way? Oh, because you removed the 4 to be true. Did I do the math wrong? If previous is removed, then degrees is fine, right? Yeah. I think this is right, maybe. Oh, I put force. I guess technically this is true because you don't have to consider the extra degree for your root. 2465. Okay. Still not right, but okay. So 0, now we have a 6. I think the min is wrong because we choose 4. The other, if we remove the other one, is going to be 0, right? Why is this? It's 4. It's 2 plus 0. It should be 2 plus 0. Force. So if we removed, okay. I mean, whether or not these will always be true, so then now we can either get true or false. Am I thinking about it the right way? Does the delta make sense? Because basically if we remove 2, we get a 6 answer. If we don't remove 2, or we remove the 2, we get 0. So 2, 0, remove is going to be 0. 2, 0, force is going to be 6. So, and here we get a -4, but it should be -6. I think we cut it the other way around. I think that's why. Maybe. Nope. Now it's -14 and 4. This doesn't make sense. Because we remove the 2. So we keep the 2. But then we lose 6. So this is going to be plus 6. This part is going to be 0 plus 2. So this is the cost of am I just doing it wrong? I mean, I'm rushing a little bit. I need to slow down. I don't know why this is wrong though. Okay, you choose -2 and it should be -2, right? -2 plus 0. What is going wrong here? Meaning that we did remove it. If we did not remove it, so the cost to keep. This is the cost to keep. This is the cost to remove. And we're trying to minimize this value. By default, we keep it. Maybe that's the thing. I don't get it. I don't get my. I feel like I'm so close, but today is that kind of story. This doesn't make sense though. I mean, I'm trying everything at this point. So, okay, slow down. You got this, Larry. You rushed too much. So we're trying to figure out. We're forced to choose. This should be right. Should be -2. I mean, this is fine. But this is wrong. Okay, so it looks at right? Okay, so 612. Okay. Why is ours 0? We don't have to remove anything, that's why. So to all these we should be minimizing the negative, right? So 2, that means that if we put it in, okay, I see. I think this is the sort key, but we need a little bit better. So this is the delta which we sort, but then we're not minimizing by that, or we're not counting for it. We want to get the cost by the rate. Delta is for, okay, you have to do both, I think. No. Well, delta is whether you choose or not. No, that doesn't make sense. Maybe it does. I don't know. We have an hour-ish. But here we're trying to figure out that -2 or 2 is the cost. Okay, so we're trying to minimize the cost, right? So okay, so I have this thing, we're trying to minimize. Do we tick or no tick? I'm just dumb today. Delta should be, no, it's, maybe that's not right. Maybe delta is fine, but then we want to keep the, this doesn't even make sense. Okay, so it's removing the 2. No, it's keeping the 2, right? So you keep the 2, but you remove the 6, so it's going to be 4. Right, but you also remove the 2, right? So why is that not getting calculated? Oh, because this is true. So yeah, you have to keep it degree 2. So this could actually be removed. Oh, because you don't have to. Why is this not 0? It is 0. So this is 0. Because you're not removing anything. But that you just not okay. I debugging the wrong thing. Because basically now you have to pop back up the thing you did remove. So okay. I mean, no, that doesn't make sense. You have to. You want to remove. Oh wait, that doesn't make sense. Why? Okay, I'm just really wrong on this one. Oh yeah. Well, I don't know why I changed that one. That took me a few minutes to debug. Okay. I mean, this is not right, but at least is it better? Nope, -4, but the other one is still 4 when it should be -2, right? Alright, let's see. Just not my day. I feel like I should have done this one much quicker, but so this is remove, not remove. Remove, not remove. Okay, that's fine. So I know you have remove, not remove. And node 0, we get deltas. So okay, so 4. So okay, so you remove, the cost is going to be 4, and we want to minimize this, right? So actually this should be subtract anyway. Okay, so maybe that's wrong though, because it's wrong. Okay, and then now you have 2 and 6. So remove 2 is 2. Okay, I see. I see what I want to do. You have to add in the thing of the rest. Okay. Okay. How do I want to do it? How do I want to do it? Do it, Larry. How do I want to do it? I see. I see. I thought I could do some delta trick, but I was wrong. I saw it right. So the deltas. Okay. So now we want to so that is to remove, and then the rest. Nope. Okay, 22 is right. Finally getting something right. So here we have, I don't know what this means. Oh, that's the sort key. So you keep, you subtract this and then you take the 0 from the other one. Okay, but then now 65 is wrong. No edges removed. Okay. So at node 0, delta is equal to 1. Why? Oh, because it assumes this, but that's why I had true. Yeah, I had, okay. So that is right, but then now this is wrong. Why is that wrong? Because if it's true, then we don't add a degree of 1, so we have 2, right? Oh, I had this as equal to 0. I don't know why, but it shouldn't matter. Oh, this is just wrong in general. I think it's supposed to be this. Yeah. So we're supposed to sum it up anyway. Okay, so still wrong. Okay, why? I'm making a lot of silly mistakes today, seems like. Because I feel like my idea was right, but okay. 0 removing 1 is going to be wrong. Why? Tell me why. Really? Degrees is equal to 3? Oh, wait, yeah. Why is this? I'm getting so confused as to why both of these cases not right. If it is not, if this is false, then we have one more to degree 2. No, but that's only if it's root, right? Previous is removed, you could find it as previous is removed. Then why is this wrong? I mean, this is right. So then now we remove degrees is 2, delta is 0. And so now we're keeping it, which is going to be 6 and 0 as removal. Oh, but we don't have to, right? We could still just tick the smaller part. So, okay. So we can, on the first one, we can remove, but we don't have to. Okay. Okay, that is still wrong though. No. Okay, so this is going to be the removal, but this is the keep. If keep is cheaper, then we take keep, right? So why is that wrong? Yeah, this is wrong because we want to keep these. Right? Delta is equal to 0, so then now these arrays are just weird. Because maybe this true is weird. Okay, let's say we're at 2. 2, it should be that we return 0. Okay. And now one of these should be a 6. So true is removed. This should be, so false is going to be, so we have 3 degrees. We want to remove 1. So delta, we want to remove 1. This is the removal cost. So false is not, so this is wrong. Why is this wrong? This is the removal cost. So you're forced to remove. Oh, I see. The other one is optional. We could remove when we don't have to, not the other way around. Larry, what are you doing? I hope this is right though. Alright. I don't know. Is it right? I don't know anymore. But I think the idea is okay. We'll YOLO submit because what else are we going to do? But yeah, I mean, I was just very silly for a very long time, I guess. How many people got it right? 84. So hopefully I move up a little bit. Or maybe the thing is just outdated. Yeah, okay. Maybe I am just outdated. 172. Oh wait, no. I mean, where am I? What 57 minutes. So actually, I guess I'm okay. About 5 minutes of penalty. So around top 100, not quite top 100. Oh, just updated to be here. Am I? I feel like Q4 I knew how to do immediately almost, and I spent, I don't know, I have to look at the video. I mean, I'm recording this live, about like 20 to 30 minutes debugging. Though, I mean, I don't know if I would call this a debug. I think we had, I was just doing the math wrong because I thought I could do it on Delta and it just would give me the number, and maybe you can, but I think I was returning the wrong things here as a result. Because I don't think I can just base it off the Delta. Yeah. But it turns out the test case was pretty good, but I don't know. Yeah. Oops. Just gonna screenshot it for the boys. I mean, not a terrible finish, but I don't know. It is what it is. A little better than the morning contest. I mean, but it's kind of rough when you know when you know you're right. Mostly. I thought I could do it like on Delta only. I guess because we have to return the min of these. Yeah, I don't know. I mean, well, I was just really messed up on this part, honestly. Like, I was returning the wrong thing for a while. This looks really yucky, though. I mean, I'm sure there's a cleaner way of doing it, but... Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, everything in between. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.